situation where multiple threads or processes read and write a shared data item, okay, sharing, and then the final result is depending on their timing of execution. So this is not consistent, the result. Okay, let's see one example of this basic source code, basic pseudocode. Okay, so we have two program 1, program 2, where program 1 increasing the value of count, while program 2 decreasing the value of count. And then the count is the shared variable, where the initial value is 5. Okay, so let's see one scenario where we start with R1. Okay, so R1 count, and then R1 increase the value. Okay, this is what happened when we have the count plus plus, and then the value of R1 updated to count. Okay, so then we have the value of 6. Then the context switch, giving turn to R2, sorry, for process 2. Okay, so the register 2 will start to count. Okay, it will get the value of count, which is just now is 6, and then reduce the value, okay, to 1, and then now it's become 5. So put the value of R2 to count, and then the value of final count is 5. Okay, so second scenario where we have like R1, okay, get the value of 5. So now the value is 5. Okay, the value is 5, R1. But suddenly it's being interrupted. Okay, so R2 now execute. So R2 get the value of count. So count is 5. And then R registered to minus by 1 is become 4. And now the value of count become 4. Okay, while on the other hand, now the R2 continue, the program 1 continue to execute. So we have the value R1 just now is 5, so it will continue from there. Okay, so 5 plus 1, so it becomes 6. So now the final value of count is 6, so it's not consistent, right? If we have this kind of scenario. So what happened, another scenario where R2 execute, where program 2 execute first, but somehow it's being interrupted. So R2 get the value, so now R2 has 5, and then process 1 interrupted, so process 1 execute, so it get the value of original value is 5, and then count the value to 6. Then R2 continue, the program 2 continue, where R2 get the value of the previous one is 5, where this minus 1 we have the value of 4. So we can see that the same scenario where we have process 1 and program 1 and program 2 execute, but if there is interruption, okay, if you're not allow process program 1 to execute until finish, then only we allow program 2, then the value will be inconsistent. It could produce 6, it could produce 4. So that's why we really need to enforce the mutual exclusion. Only one process to execute in the critical section. So we can say that the count plus plus is the critical section. Okay, because we are sharing the value of count. Okay, so I'm hoping that you're able to relate the critical section and also rest condition. The last term based on the table is starvation. With starvation condition where the process is not getting the requested turn. Okay, so where the process is being overlooked by the processor. Okay, so process should be like process 1, process 2, process 3, but somehow it's overlooked and then miss process 3, so meaning only one, process 2, process 1, process 2. So process 3 doesn't get the turn, so this is what we call starvation. Okay, this slide showing you the example of another scenario of critical section, okay, where we have process A and process B competing for might be printer, using printer. Okay, so when process A is using printer at this point, starting to use, one along the way using the printer, somehow the process B asking permission to use printer. So in this case, B should be blocked. Process B is not allowed until process A finish. So you can see that until the process A finish with the printer, then B is allowed to use printer. So this is what we call mutual exclusion, where we only allow one process to be in the critical section. Okay, to be in the critical section. Until finish, then we allow B to use the critical section, because the printer is considered like as the critical section because we share the printer with other processes, right? Okay, let's see another scenario where we have this shared critical section. If we can look at the critical section now, is C in, okay, where we asking for input. Okay, so like in this example, we have two processes that currently running this particular program. Okay, process 1 giving the input of 10, right? Suddenly it's being interrupted, and process 2 continue to use. So it will execute from the beginning. It's setting the value of 5, giving the value of 5. Then when process 2 printing it out, then it will get 5. So this is the correct output. Somehow when process 1, okay, continue, so process 1 will get the value of 10 or 5, because this is the shared source code. So it will basically, okay, now the value of A is being changed to 5, so the output will be 5. So this is why the concurrency must be controlled so that the value is correct throughout the execution of the process. Okay, now we see the principles of concurrency. Okay, so it should interleaving, so meaning we can switching from process A, process B, process C. Okay, basically we can set it to time out. Okay, and also overlapping. Overlapping means in the multi-processor environment where we could execute two processes on different processes. Okay, we have two, right? So we can execute two processes at maximum. Okay, so in uniprocessor environment, okay, the speed of execution cannot be predicted. Okay, so it's depend on the activity of other processors and how the OS handle interrupts, and also the policy of scheduling that being used for that particular operating system. Difficulties of concurrency, we are looking into 3, which starting with the sharing of global resources. So for example, I show you the process just now, two processes sharing the same global variable. where both of them write and read on that particular variable. Then the order of sequence is very important. Okay, since if we are not control the sequence, the output will be unexpected, something that we are not expected to be, right? A second difficulty is in how to manage allocation of resources. For example, OS already grant one resource to process A, for example, but somehow process A is being suspended, bring it into virtual memory. So what happened to that resource? So operating system cannot basically let the resource being locked because it's not being used, okay, by process A. So this is the difficulty of operating system. And the third one is how to locate for any programming error. Okay, so and also it's difficult since the result you cannot simply reproduce the result. So these are the three difficulty even in uniprocessor, okay, which we are going to see more about these concurrency issues. All right, next is race condition. I'm sure that this is clear enough, so I just keep this slide. Okay, so these are the operating system concerns, okay, where the operating system must able to keep track of the various processes. Okay, so I think this is done. It's already you're already clear about the PCB, process control block. So where this is the platform for the operating system to track of the processes, right? And also OS must allocate and deallocate resources for each active process. Okay, so at time, because processes will asking for resources such as processor time, memory, files, and also I/O devices. Okay, the third one is the OS must protect the data and physical resources of each process against unintended interference by other processes, because we have lots of processes in the memory where each of them having the rights to execute. Okay, we have the sequence, so that's why we need to make sure that there is no interference between them. Okay, so all the techniques is related to the memory, files, and I/O devices, which we will go through in the next topic. And the fourth one is regarding the functionality of OS, which able to function, okay, the process and the output it produce, okay, where it's independent by the speed of the processes, right? So this is the one that we will cover in this topic. Next